Hello everyone. Today I'm going to present the paper EEG-based stress detection and personalized music recommendation system for stress relief. This is presented to you by Srijit Bhattacharya, Catharine, Parmar, Nathan Lee, and our project guide and mentor, Dr. Mohammad Husain. So without further ado, let's dive right into the topic. To introduce this topic, I would like to say how stress has become an important aspect of our lives every day. Stress happens to everyone and it does take a toll on our mental and physical health. With the growing worries about stress, we need a real-time accessible stress management tools, and our research attempts to actually find a way on how we can quantitatively measure this stress and utilize music therapy to reduce it. To integrate EEG stress detection into our personalized music therapy, that's what this paper is based on. The objectives include measuring of our stress using an EEG brainwave analysis, recommend personalized music to the participants to reduce their stress, and use machine learning to detect stress levels. This can be validated using effective EEG and feedback. To give a brief system overview, we will be collecting the EEG signals during a timed cognitive task, and this will induce a certain amount a degree of stress into our participants. We calculate the alpha power and the beta power ratio from the wavelengths that we collect using the Emotiv headset, which you can see below, and the green spots are the electrodes on our cranium. Machine learning is used to estimate perceived stress scale or PSS score. This is something which our participants need to fill up beforehand. It's a 10 questionnaire data set which actually was developed by uh, Cohen, and it is called the perceived stress scale. If you see the picture on the right, you can see three bands. 0 to 14 is low stress, medium stress is 14 to 26, and high stress is 26 to 40. Based on your answers to the 10 questions, you are assigned a number, and the number indicates how stressed you are. These We asked our participants to go through this PSS test and self-report their test scores before undergoing our timed cognitive test. And post EEG analysis, there will be a music played for our participant as per their as per their past choices on Spotify, and we'll see how this affects their alpha and beta power ratios.
We'll be looking at related work on EEG-based stress detection and music-based systems to understand the scientific foundation of our project. In the paper by Hamidpur et al., self-reported PSS scores were used as ground truth data to train EEG-based models. They demonstrated the feasibility of using brainwave features, particularly alpha and beta wave ratio, for stress level classification. They also reinforced this approach by validating how cognitive stress correlates with changes in EEG signal power. On the music side, the study done by Salimpur et al. Classified song based on emotional attributes such as valence, arousal, which we used in our clustering approach. They also developed a music recommendation system that aligned track selection with individual user preferences. The paper done by Cole highlighted how music acts as a medium for emotional regulation and stress relief, supporting the therapeutic potential of our system. The foundational study done by Jaslyn et al. Discussed how emotional responses to music are mediated through psychological mechanisms such as arousal and valence. This informed how we selected audio features for relaxation. A paper done by Sorina et al. proposed an adaptive system that modified music in real time based on EEG input alone. This work laid the groundwork for combining EEG signal processing with emotionally intelligent music curation.
So for the experimental setup, we have 6 participants, all of them belonging to the master's degree course in our university, and we had some pre-test instructions like no caffeine, no alcohol, and no vigorous physical activity. We wanted our participants to be in a calm state of mind and body, which levels the playing ground for them while attempting the test. Each of these participants was also asked to take the PSS questionnaire independently and report their scores. While the cognitive test, the EEG was recorded using Emotiv EEG headset. For the for the data collection, we had 1 minute time cognitive test to induce stress, and the EEG data was collected for this 6 seconds. This 6 second data went through an independent component analysis to get rid of any kind of unwanted physiological movement like head from side to side or twitching of the eyelids or even blinking, because we want our data to be as less diluted as possible. The EEG data was divided into 3 second windows, which means that we had 20 data points for our datas. And on the right, you can see that we see these 20 data points for alpha ratio and beta ratio for participant 1. We only extracted the alpha and the beta waves since our experimental process uh, aimed on using these two, but there are like gamma and beta, theta waves as well, which have also widespread utility, and a lot of work is being done on utilizing them for stress and other kind of neurological studies. The machine learning models we have used, we'll discuss about them here. It is used to predict the PSS from the alpha and beta ratios calculated for each of our participants. So we let the PSS scores reported by the participants as our ground truth, and we calculate the alpha and beta data points to quantitatively measure our stress in the PSS scale range. We have used a support vector regression SVR, k nearest neighbors KNN, random forest and XGBoost, and we have also used a linear regression model along with ridge and lasso regression to for this. We evaluated the model accuracy using the mean squared error and the R squared. The best model from the data set we had was the XGBoost. However, I'm sure that this is just a proof of concept, and with more and more participants and more data, we might have some different results for this one.
We'll be looking at the design and structure of our music recommendation system, which aim to match emotionally relevant song to each participant preferences. To build the system, we used a publicly available Spotify Kaggle dataset that includes song level audio feature such as balance, arousal, tempo, and danceability. These features are widely cited in affective computing literature as reliable indicators of emotion content in music. We applied k-means clustering to group songs into emotional clusters. Once clustered, we computed cosine similarity between participants' submitted favorite songs and the dataset to identify musically and emotional similar tracks. We asked participants to submit their top 5 favorite songs via web-based interface, and this preference served as a seed data for generating a personalized playlist. This method ensured that recommendations weren't just generic but also grounded in individual emotional associations with music. Our goal was to recommend tracks that not only sounded similar but evoked comparable emotional responses for each users. In this section, we'll be looking at how the clustering algorithm visually grouped songs based on their emotional and musical attributes. Using the extracted audio features, We employed k-mean clustering to separate songs into distinct groups, each representing a general emotional state, such as calm, energetic, or sad. This visualization, displayed on the slide, illustrates how songs were grouped using dimensionality reduction techniques, um, enabling us to evaluate the cohesion and separation between the clusters. This clustering step was important because it allowed us to map user preferences onto a structured emotional landscape. Songs from clusters that align closely with the participant submitted favorites were then shortlisted for recommendation. This visualization helped validate that emotionally similar tracks were indeed grouped together, thus enhancing the emotional congruence of our music therapy phase. Next, we'll be looking at the music therapy phase where we evaluated how the recommended song influenced participants' stress level through EEG analysis. After the personalized playlist was generated, participant listens to 5 tracks sequentially in a calm setting. During this session, EEG data was recorded once again to monitor brainwave activities in real time. The alpha to beta power ratio, previously established as a stress indicator, was used as the primary feature to assess relaxation. An increase in alpha relative to beta generally suggests a transition from a stress to relaxed state. By comparing pre and post therapy EEG signals, we were able to quantify the calming effect of the music recommendation. This phase was crucial for validating that our system could not only detect stress but also reduce it through personalized interventions. In this slide, we'll be looking at the evaluation metrics used to measure the performance of both the machine learning and music recommendation components of our system. First, we evaluated the clustering performance using the Silaud score, which came out to be 0.71, indicating strong cohesion with clusters and clear separation between them. Next, the recommendation system precision was calculated at 0.53, suggesting that more than half of the suggested tracks were perceived as emotionally relevant. Participants also rated the usefulness of the recommended music. On average, users found 1 to 4 songs out of 5 to be emotionally and contextually appropriate. This mixed but generally positive feedback confirms that our initial matching algorithm performed reasonably well. Although there is still room for improvement in personalization and diversity of the recommendations.
As a part of my study and research, we calculated the PSS scores versus the alpha power ratio and the PSS score versus the beta power ratio. Alpha waves are associated with meditation, a sense of calm, and everything. So there is an inverse relationship between PSS score and alpha power ratio, which means that the higher the stress, the lower is the alpha power. And for beta power ratio, it's exactly the opposite. For uh, for beta power ratio, beta waves being associated with high thinking, cognitive stress, higher the PSS score, the higher is the beta power, because when the beta power is more, it means you're just more stressed. We tried to show this using a trend line graph on our side, and you can see that for the alpha power ratio and the PSS score, um, it's a good trend line which shows the inverse relationship. But for the beta power ratio, I'm sure with more data points we'll have a better result. But as of now, we are content with moderate direct relationship between PSS score and beta power ratio. So higher stress, lower alpha, higher beta, and lower stress, higher alpha, lower beta. This is a graph which compares the alpha and beta power ratio before and after the music therapy. It shows that the one in orange is the stressed ratio, and the one in music is the one in blue is the music ratio. It shows that there's a slight improvement. However, We are aimed at collecting more and more data for this and support our uh, hypothesis. The limitations of our work include the small sample size. We would like to add more and more participants. Also, our participants were from uh, a master's degree course, which means that they had a certain degree of academic prowess. We would like to include more participants from the different strata of life and a standardized test to actually make sure that we are doing a level playing field for everyone. We have only used alpha and beta waves. In future, we would like to add theta and gamma waves as well, because it further expands the domain for our research. And we are also like subjective PSS ground truth, which were reported by the participants themselves. Limited music features like no lyrics or genres, that's something we would like to work on in the future as well. While the scope for this domain is absolutely huge, and we would like to keep working on this, but again, more and more technologies are arriving every day, and this just means a bigger scope. We can expand our EEG features, external test markers, improve precision via hybrid context models, and we can also use real-time adaptive EEG feedback for dynamic playlisting. On the right, you can see UI UX of a app that one can imagine to have, which is a real-time indicator of stress. However, it is always beneficial that in terms of in case of prolonged periods of stress, medical help is consulted. Conclusion for this is that EEG features can estimate stress. Personalized music shows measurable stress relief, and our project has come with a dual objective, which is detect, quantify, and reduce stress, and it has a promising approach for mental and wellness tech. Thank you.